Hi, everybody. My name is Rita Barrios. I am, as James has mentioned, I am the Associate Director of Vehicle Cybersecurity at University of Detroit Mercy. In addition to that job that I have, I am also a Senior Cybersecurity Engineer for Bosch Automotive. As James mentioned, we're in the Metro Detroit area, so we are heavily into the automotive space, into autonomous vehicles, electric vehicles, all the suppliers, tier one. Bosch is a tier one supplier. I currently work on advanced driving systems or autonomous driving systems to secure those. And I work across products. So currently I'm working on a Ford product as well as a GM, as well as a Lucid product. So we do move across that. In my spare time, I am chair for the Society of Automotive Engineers, document J3201, which was just published on credential and key management systems within the vehicle. And I also teach Introduction to Vehicle Cybersecurity at Detroit Mercy. And so today I'm going to talk with you about vehicle cybersecurity and how it's really evolved. And it started, and I'll get more into this in the presentation, but as soon as the vehicle became connected, that's when we started really thinking about cybersecurity. And a lot of people think it just happened over the past couple of years, but really we've been thinking about cybersecurity since about 2013, 2014 in the vehicle space. So it is becoming a rather matured space. I'm gonna share a presentation with you. And let me go ahead and get that started. And okay, hopefully you can see my presentation and get some of this stuff out of my way so I can see. So as I said, we're going to focus on vehicle cybersecurity, and it's not much different than what you've already learned about cybersecurity. And this presentation is geared towards first-year students. So if it's redundant of what we're going to talk about, let's look at it as just being a slight refresher. So basically, what is cybersecurity? And the basic definition is that we want the protection of internet-connected computer-based systems and their components. And I really want to highlight this components, because not only are we talking about the modules themselves and the what we call the ECU, or the electronic control unit, the hardware, but we're also talking about software, data, and people. And in our connected vehicle space, not only are we talking about the data and the people and those things, but we're also talking about those back end, what we call enterprise systems that the vehicles are connecting to, as well as electric charging stations and those things. What we're protecting against is the unauthorized information disclosure, transfer, modification, or destruction of those systems and the whole entire ecosystem, whether it's accidental or intentional. And I really want you to keep in mind that we're talking about unauthorized usage. And we're gonna dive a little bit deeper into what that means. Of course, we're gonna focus on, even in vehicle cybersecurity, we focused on the CIA triad, confidentiality, integrity, and availability. Even when we're doing our threat modeling on the vehicle level, we're still looking at those three primary components, but we've expanded it out a bit as well to include identity and to understand authorization and authentication. So confidentiality says that we're going to only give access to those systems to those people who are authorized to have those access. And they're going to be put under agreements to not disclose it as needed. One of the big problems that we have, and this is across the board, whether it's an enterprise IT system or a vehicle system where we're developing software and firmware for the vehicle, is the insider threat. And so authorization to those components becomes paramount importance. I was just reading an article today about an insider threat at Tesla, where the insider disclosed a tremendous amount of data to the media in Germany. And so we're going to see where that falls out. It was just came in one of our information sharing newsletters today. So we're going to be keeping an eye on that. We also look at integrity. In other words, how good is the data? How can we trust that data? And we want to make sure that that it's free from unauthorized modifications. We also want to make sure that the data is very complete. Now, let's think about this in a vehicle system. If you have an autonomous driving system, if that data, say that location data coming in from your radar sensors, on typical vehicle, there's anywhere from 6 to 10 radars. All of that radar information needs to communicate with each other, and it needs to be synergized so that they're all saying the same thing. So if we have incomplete data, that means that autonomous driving system can no longer do its lane changes and its automatic braking and things of those natures. So integrity is really important in the autonomous driving space. And then, of course, availability, making sure that that ecosystem is available. Not only that the vehicle and that it can drive where it needs to drive to, but the GPS system, the cellular system, the radars, the lidars, the ultrasonics, the cameras. Tesla vehicle operates completely on camera data for its automated driving. And one of the problems we have with Tesla is integrity on that camera data. You've all heard about the Tesla crashes into emergency vehicles. And the reason being is those emergency vehicles' lights are so bright that it blinds the camera. In other words, it breaks the integrity as well as the availability of it. So we want to make sure these systems are used as they are intended to use and in their intended environment. In a vehicle system, this is incredibly important, and we talk about something called functional safety, and that says that make sure the vehicle is safe to drive in its intended state. And so availability, we extrapolate that out to include as intended in their intended environment. So it's really not anything different than what you've learned about in enterprise cybersecurity. We've just extended it out to this, if you will, this computer on wheels. So what's the difference between authentication and authorization? People often use these words interchangeably, but they're not really interchangeable. Authentication says that we are validating that the identity of the entity is who they say they are, or we're verifying it to be true. And we're going to call it an entity versus a person, because in my vehicle system, all of my components authenticate themselves to each other. A radar authenticates itself to a body control module, or a camera authenticates itself to the ADAS unit, and even your locks on the car doors in today's vehicle authenticates itself to the vehicle as well. Those are all attack vectors. And so we want to make sure that there's no rogue components on the vehicle. In contrast to authorization, authorization says that this authenticated entity has the ability and the access to do what it's needed to do. We take the least privilege approach and authorize only what's needed at the time that it needs it. And so on a vehicle, we've all heard of root access. On a computer system, vehicles have the concept of root access as well. We have real-time operating systems. And so we want to make sure that nobody has true root access. But if a component needs to have that level of authority, it's given that level of authorization for only a small amount of time to do its job, and then that's taken away. Much like in the enterprise system, a lot of this is not going to be new to you if you've been focused on enterprise systems versus embedded systems. So authentication. In order to have strong authentication, we must validate two of the following characteristics. And when we talk about authentications, keep in mind that these things that we're authenticating to can be human or electronic. We do use cryptography, and we do have passwords and tokens and digital signatures. So in order to get that strong authentication, I have to have something you know, something you have, or something you are. Something you know is like your password or your PIN number. Something you have is your key fob, your cell phone. We do use cell phone as a key now. We do unlock and start the vehicle on approach. And Nissan has just implemented where you can start the vehicle by sitting in the vehicle using some biometric data to do that. So again, something you are for that aspect of it. And so we do focus on those strong authentication privileges. As we move the vehicle into more of a service, and the vehicle is really software. It's the software-defined vehicle. Features are going to be turned on and off for pay in the not too distant future. And BMW is already doing that with heated seats. If you want heated seats at BMW, you have to pay for that service through the computer screen in your vehicle. And so we're going to be looking more so into more biometrics in order to make that happen. We also have to understand when we're talking about cybersecurity, the differences between vulnerabilities, threats, and risks. Just because I have a threat or a vulnerability doesn't necessarily mean that I have a risk. I have to have both of these things in play in order to have that risk. And a threat is any incident with potential harm to the system. And this could be your insider person. It could just be a bad software update. It could be a failed update. Sometimes updates happen just like on your laptop. Sometimes an update will happen and it'll a partial update and we'll have to go back. That's a threat as well to the availability and integrity of the system. And then we have to have the vulnerability, which is a known weakness that a hacker could exploit. And I'm going to say could exploit because not all vulnerabilities are worth the time or effort to hack. And it really depends on what the value is to that hacker. Once we have a threat and a vulnerability, we end up with a risk. And this is the potential damage that a threat exploits a vulnerability. So when we're looking at vulnerabilities and threats in order to develop countermeasures to reduce this risk, keeping in mind that we're never going to get to 100% secure, all right? If anybody tells you that they can get you to 100% security, I would question them, because when we're doing countermeasures, it's based on what I know today. I can make a guess, an educated guess on what might happen tomorrow. But again, it's only going to be an educated guess. So we build for today, strong enough for the near future, but we can't go so far out as to even a year from now on what that landscape's going to look like. When we build these countermeasures, the first thing we do when we do threat modeling is we identify the threats that exploit the vulnerabilities that leads to a risk, and then we define those mitigations which reduces the risk. And it is a living cycle. Anytime the software changes, the environment changes, the connections change, I have to go back and re-look at my vulnerabilities, my threats, and my risks. Now, risk can be either tangible or intangible. Tangible meaning the loss of money, loss of life. When we're talking vehicle systems, we absolutely look at the loss of life. Or it can be intangible, and this would be reputation. Like Tesla, the autopilot crashes into emergency vehicles. And so Tesla takes a hit on that reputation because of it. And that means loss of business for them. And so if safety is of one of your top importance in purchasing a vehicle, you're probably not going to look at a Tesla autopilot. So who are the threat actors? Who are the hackers? They can be individuals. They can be corporate entities such as an insider threat. They can be universities, the people that are doing research. They can be terrorists or nation states. And it really all depends on what their motivation is, right? You know, just like any criminal activity, you look for motive, means, and opportunity. And there always has to be a motivating factor in it. From a university point of view, the motivating factor is research. You know, they want to go to Black Hat or DEF CON and push them through research. For a terrorist, they want to cause damage. You know, nation states, they want to take control of a political system. So, and again, depending for a vehicle system, expertise is incredibly high. You have to know vehicle systems. You have to know networking. There's networking in the vehicle. It's a little bit different. We'll touch base on that just as a little bit, just because we simply don't have time. I usually teach this whole course over 16 weeks. But, you know, and time is really important. Typically, the individuals in the universities, they'll go out to eBay and buy a component, and then they'll reverse engineer it and do all sorts of things. And they have a lot of time to do that, you know, versus a corporate. Typically, corporations, we're going to find insider threats. We're going to have to find somebody, an angry employee. Tesla, again, the gift that keeps on giving, got hit with that as well. One of their engineers launched some malware into the vehicle. Nation states are going to be looking more for like power grid access, you know, to the factories, the IoT. They want to bring down the GDP, or the gross domestic product, which automotive is about 5% of gross domestic product. And again, what's their goals, you know? And it really depends on the individual. Consequences of them are brand damage, liability, legal actions, and for an automotive, up to and including criminal activity should somebody pass away because of a failure on the automotive side. There have been engineers that have spent some time in jail on the functional safety side for hiding things. If we look at the airbag problem with Takata airbags, there were some engineers that actually went to jail for that. Then economic loss, for us, it's recall. We never want to have vehicles recalled. It costs a lot of money. And then ultimately loss of life. When we're dealing with an autonomous vehicle that's driving down the road at, I don't know, in Michigan here, we can go upwards of 70, 80 miles an hour in the Upper Peninsula. You basically have a weapon of mass destruction running down the highway. If it loses control, there's going to be damage. There's going to be loss of life. And so we want to make those as safe as they can and as protected as we can. So when I ask people who are the threat actors, who do they think is the biggest threat actor that we know of? I don't know if anyone can shout something out if I can hear you or what, but I'll give you a minute. So our biggest threat actor is corporate. It's people like me, right? I have the keys to the kingdom. I know exactly how all these systems work, how they interchange. I know where their weaknesses are. I'm the senior cybersecurity engineer. I do the threat modeling on the advanced driving systems. I know where the weaknesses are. And so you have to be careful of me, and you have to put authentication authorization around what I do so that I cannot move code into production. I can go to other engineers and say, we need to do X, Y, and Z, but I can't actually move production level code into a vehicle. I'm not authorized to do that. There's other engineers that do that. And so you really want to do the separation of responsibilities, you know, to protect your systems internally. So why does it matter? So when we're looking at why does it matter, there's 4 factors that we look at. We look at what is it that we're trying to secure and why, because not everything needs to have the same levels of security. An advanced driving system has high degrees of security. A door lock, not so much. You know, we do secure the door lock so that you can't gain access and move laterally, but that's about all we're going to do until we use phone as a key. You know, I have my iPhone and I can use it to unlock my door. That's when it changes, you know? So again, depending on your environment, you're going to change things based on what that threat model is going to come out. The other factor we consider when we're considering what it is and why we're securing is what are the economics of the stakeholders, both the victim and the attacker. What does the victim have to lose? So what does GM have to lose, or Tesla? And what does the attacker have to gain? And so when we're doing our threat modeling, when we're analyzing risk, we take those into consideration as well. Social influence, this is where we see a lot of the research hackers coming out at DEF CON and Black Hat, because it's important to them to go very public and very wide. We at Bosch, we have actually a researcher that is going to found vulnerability in one of our components, and they're going to be presenting it at Black Hat this year. So it goes very far and very wide. And so we need to respond to that as a corporation. So our stakeholder is that it's brand, it's reputation. For the attacker, they're going to, or the researcher, they're going to present it at DEF CON, or I'm sorry, at Black Hat. And so it's going to be viewed by literally hundreds of thousands of people, which increases our risk because of that. And then, of course, public policy. In the vehicle space, we have a tremendous amount of standards and regulations through NHTSA, the National Transportation Highway Board. And not only in the United States, we have regulations in Europe. We have what's called the European Union, which is 17 countries. We have regulation in China. So basically the whole globe, depending on what geographical region you are, you have different regulation standards and laws. And we must abide by all of them because that's our market, right? As Bosch Automotive, we sell components literally all over the globe, not only for vehicle systems, but for household items, heating and cooling, power tools. You might in your home have a Bosch refrigerator that's connected. Those require security as well. But so as a company, these regulation standards and law become basically our Bible. Keep in mind though, regardless, whenever we're considering security, the first thing that we consider is regulation standards and laws. Then we consider safety and then security. And if I have to forego a bit of security to meet the standards, regulations, and laws and safety, I will do that. So I will downgrade security because my priority, of course, are the regulations and standards, then safety, and then security. And I know people often balk when we say that, but if I have to decrease security to make the vehicle safer, then I'm going to have to do that, right? Loss of life is the most important. So automotive cybersecurity, I'm hoping you guys can, here, let me check my time here. I'm hoping you guys can, we're going to watch a bit of this video called How to Hack a Car. And it's a bit long. I will post out and give James the slides so that you can watch these videos as well. This is from, as I said, 2015. And if we can hear it. Someone give me the thumbs up that you can hear the video.
I don't think we're hearing it. Yeah, I don't see an audio source option here, unfortunately.
It would be on her end because
Can you guys hear it?
No, we can, Dr. Barrios.
Okay, let me see something.
The audio from is going to be on her end, basically it's capturing her mic, but not the audio from her computer. Therefore,
Okay.
Oh, yeah, on Zoom, did you check the box to share audio when you share your screen?
I believe I did. Let me just double check. Yes, I am sharing sound from my computer. Let me give it a try. And if we can't, then we can't.
And you can do this from outside the car?
I can do it from a mile away.
Oh, really?
Were you able to hear that?
Yep.
Okay, perfect.
When you drive an automobile today, you are driving a big computer system that happens to have wheels and a motor. There's almost nothing in your car that is not mediated by a computer. When you step on the gas pedal, it is not directly controlling
Oh, sorry about that. I'm trying to
the
get
fuel
that.
oxygen mixture. Rather, it is telling a computer that you, the driver, wish to go faster, and then it decides the right way to do that. Not only are they networked to each other, so that the brakes can talk to the engine for stability control and so forth, but they're also networked to the outside world. Effectively, your car is on the internet.
The CAN network, or CAN bus, is a network within the car that allows all the pieces to communicate. Everything can read and write to the CAN bus and pretty much is always listening for commands from the CAN bus. It is not easy to hack a car. The sophistication level is pretty high. Each car has a different language, each piece speaks different words, and not all those pieces have been mapped publicly. Cars have the same kind of chips that computers and cell phones have. All of these parts can be bought online for relatively cheap. You use these to plug into portions of the ECU. You can communicate directly with the ECU or with the mobile chipset and tell it to run commands that you want. Tell it to increase the amount of fuel that it's getting. You can tell it to go faster, release the trunk, hit the brakes.
There is not a motivation, aside from simple theft, that would necessitate developing the skills, which are not insignificant, required to do this. Then there's a surveillance aspect. We showed how we could remotely track the car and listen to what was being said. That said, there is not a terrible threat right now, in part because the cost is high. As the pieces of hardware required to experiment become more readily available, as there's more literature explaining how it works, as the cost goes down, then people can be more innovative in how they might take advantage of it.
I'm Alberto Garcia Higuera. I'm from Spain. I work in cybersecurity.
And we made a piece of hardware that we have right here. It is called CHT, car hacking tool. Yeah, it's not very original, I know.
We were invited to Black Hat Singapore to show our last research, the CHT device. You just have to put these two wires in the campus network. That's it. It costs $25. You can buy the components any place. Right now, the size of the CHT is like an iPhone, more or less, but it can be smaller. Car hacking is a very interesting field. People don't think about security. You can connect from your house with your computer to your car. That's really scary. You can just walk by and just implant the device. So imagine that I just go and approach to a car, I connect the CHT, and I just go to my home. I can control the car. It's very easy. Once you connect it, you can just remotely use it to manipulate anything. You can just notice that your car is going to the right and you are not turning the wheel. You can activate the handbrake. When you do this thing, you are just sending some kind of packet to a network saying, hey, wheels, stop. If you turn on the lights, there is a packet that's gonna say all the time, I'm on, I'm on, I'm on. Imagine that you are just driving at night. If we are able to drop the on packet and just insert our own packet saying turn off, turn off, turn off, the thing is that the lights of the car are gonna just turn off or turn on whenever we want. It's very, very scary. At the end, you can generate an accident.
Worst case scenario is someone completely controlling your car, control your brakes, control your steering. You could definitely break or blow up portions of the engine. Nothing's ever fully secure. If someone's dedicated enough, it'll always be a cat and mouse game.
We have to secure that entire ecosystem. It used to be you lock the doors on your car and your valuables in your car were secure. Today, when you lock the doors on your car, your personal information is actually stored out at another cloud services. All of a sudden, that has a physical impact on our lives.
Many of the standard things we would do on a PC to make the software secure, none of that was being done, zero. And so the kinds of bugs that we would find really, like, it almost felt like software archaeology. It's like this was the kind of bug I would find in a PC back in 1993 when the internet had first taken off. From a Darwinian standpoint, they had never had to face adversaries, and so the code never had to be hardened against that. Now is the right time to identify if there are problems before there are people targeting them.
So I'm going to stop there because I don't want to take the whole class period watching this video. So like I said, I'll give James the slides and he can distribute. And the videos are embedded in there, so you should be able to watch them and rather than search for them. You notice that the researcher said that there's really not a market for it. And again, this was in 2015. In 2023, it's a huge deal right now. Because we're moving more towards autonomy and more towards electrification, where the electrified vehicle actually connects up to the power grid. Power grid's a big challenge for not only us as a user of that power, but for the nations themselves. Stop. I'm gonna go to the next. There we go. So the researcher in the video was talking about something called an electronic control unit. And there's anywhere from 70 to 80 upwards. Some of the more advanced vehicles now are running about 100 electronic control unit. And you can imagine that an electronic control unit is kind of like the motherboard in your cell phone, all right? You know, there's an electronic control unit in your cell phone or an ECU. So there's about 100 of these in the average car today. They control everywhere from advanced driving systems to tires to, you know, that light that comes on that says you have a low tire. There's a sensor in your tire that's connected to an ECU that sends this information into the body control module, which sends it to your in-vehicle infotainment system, or what we call the cluster, which sits behind the steering wheel. There's for your engine, it controls gas, it controls the emissions, the harmful gases that come into your car. It'll let you know those things. There's one for GPS and cellular, so on and so forth. Just about everything a vehicle is doing today is moved more away from being controlled by mechanics to being controlled by software. And so that's what we're talking about, the software-defined vehicle. And if we can look at vehicles, and when we talk vehicle, we make no distinction. Most of the time we're talking about automotive vehicles, but it could be an airplane, it can be a truck, it could be a fighter jet, it could be a semi-truck, a motorcycle even. You know, so a vehicle is a vehicle is a vehicle. All of these things have software in them now. The 787 Dreamliner has 7+ million lines of code. The F-150, 130 million lines of code. This is the Lightning. This just came out last year. The F-22 Raptor, 2 million lines of code. All right. So really, we are talking about software as component of this thing that's on wheels. And so, as the author said, basically you're driving a computer on wheels, or you're flying in a computer on wheels if you're on a newer airplane. And with electrification, that brings a whole new ballgame to this thing called software. So in the vehicle network, we have something called a CAN. It's a contained area network. And basically, if you're familiar with any type of networking, this is very familiar to you. There's a packet that comes through. So you go and you hit the fob, the button to unlock your vehicle. A message gets sent from that fob to the controller and the door lock. And that controller then sends a message onto the CAN network that says, vehicle, unlock the doors. And it's set up like any other network package. You have your control information, you have your data, this has headers and so on and so forth. You have your redundancy check, you have your acknowledgement, and then your end of frame. And just like a network system that your computer connects to the internet with those packets going back and forth, you send a packet, you get an acknowledgement. The same thing happens in this vehicle system. As you can see, the color coding here, the anti-skid brake system, this is where we see that coming into play, which is running on Ethernet and CAN. So red is CAN, blue is, we have CAN high, which is faster, or CAN FD CAN, as well. And then we have CAN low, which is a slower speed. And so we'll have low level modules on here. We have FlexRay, which is another type of networking. And of course, we have Ethernet for all of our connectivity to the satellite systems, to cellular systems. But then we have this thing here called the OBD2 port. The OBD2 port, or onboard diagnostic port, allows you to plug a computer into your vehicle. Now, the law, remember, we always follow the law, says that people have a right to repair their vehicles. And so oftentimes, if you ever watch any racing, like whether it's NASCAR or Grand Prix or anything, you'll see people out there with the computers plugged into the vehicle, and they're plugging in through this OBD2 port, and they're calibrating the vehicle, and they're calibrating how much gas flow goes in, the sensitivity of the braking system, so on and so forth. But it's all being controlled by this network. And it really depends on what it is we're trying to do. Components get placed on the network depending on what they have to do. Higher end components are going to be on high-speed CAN versus low-level components, where we have an oil supply or a powertrain things. And so entry points for hackers, let me check my time here. Entry point for hackers are just what you imagine them to be. We have the standard external Wi-Fi, key fob, LiDAR, tire pressure monitors. That's always a fun thing to go through. The tail light. Recently, somebody was able to gain access to a vehicle by going through a headlight. And basically, they pulled the headlight and plugged into the network. And so they did a man-in-the-middle attack and was able to move laterally through a vehicle. And I'm not going to tell you which vehicle that was, but it's something to consider. Things that we were thinking so simple that nobody would want to do now become attack vectors. We talked about the OBD2 port, auxiliary input. How many of you plug your phone into your car to charge it? USB devices, cellular devices. Mobile device pairing is an interesting thing because now once I pair my mobile device to my vehicle, now those two can communicate, and both of them have to be secured to keep the mobile device secured and to keep the vehicle secured. If I have rogue software or an application on my mobile device, it has to be prevented from gaining access to this vehicle. Remember, we were talking about authorization, authentication. So these are all the components. They're not all the components, but it's a fair representation of all of the things that come in. Newer vehicles, the ones that are going to be coming out in 25, I'm actually working on vehicles in model year 25, 26. Newer vehicles in model year 25, as we move closer to level 3, level 4 autonomy, are going to have a camera in the vehicle, a driver-facing camera. And as you can imagine, there's a lot of privacy concerns there. The reason the driver-facing camera is there is for level 3 autonomy, the driver has to be alert. And if the driver is not alert, then the autonomous features shut down. And so that the driver has to take over. And so the driver monitoring is going to be happening. So what could go wrong? Well, everything can go wrong. It's just a computer, right? It's a stupid computer. We can do theft, we can do terrorism, we can do ransomware, all those things. As we said, automotive security events really started, if we look back, it really started in about 2010, and GM OnStar was the first one that got the remote control. And then we move over to, and this is actually out of date, 2017, that the Tesla was hacked by a researcher. And of course, the Jeep hack. This was the shot heard around the world. And I don't know if you've ever heard of it, about researchers were able to take remote command and control of the vehicle while it was driving down the highway. So, and this is the Jeep hack. Let's see how much time we have here. We'll watch a little bit of this Jeep hack because it's sort of interesting. So again, this is 2015. This is the second time they hacked it. The first time, it wasn't remote. They were wired into the vehicle. This time it was all remote.
It's not fun to have your 2-ton SUV's brakes hacked just as you're parking in front of a ditch.
Okay, hold on tight. Hold on. Oh,
That's what I've learned from Charlie Miller and Chris Valasek, a pair of hackers who have spent the last year developing a piece of software that can wirelessly sabotage this 2014 Jeep Cherokee. It hasn't been altered in any way. There are no devices attached to it. But like many thousands of Jeeps around the world, it can be remotely hacked over the internet through a cellular connection to its entertainment system that would allow someone to take over its steering, its transmission, and even its brakes. To demonstrate that, I'm going to act as today's crash test dummy and drive it on the highway here in St. Louis, while Charlie and Chris hijack its digital systems from Charlie's house miles away. They wouldn't tell me what they had plans, but they assured me that it wouldn't be anything life-threatening.
Remember, Andy, no matter what happens, don't panic.
It's not the first time I've driven a car while it's being attacked by these two hackers. But in 2013, they were in the back seat, and their laptops were wired into the vehicle through a port in its dashboard. Now they're sending the same sort of attacks remotely, and I have no idea what they might do.
He's going as fast as I've seen him, so.
So first we're going to turn the fan on him.
Yeah, let's turn the fan on, see if he even notices.
All right, something just turned on, all the fans and AC and stuff. I didn't do that. The trick started small. Oh my God. There's a picture of Charlie and Chris in tracksuits that just appeared on the dashboard. But as I drove down the interstate, things started getting unpleasant and very loud. Perfect. I can't turn it down.
This was such a fun video. Steve Logan got to enjoy it.
And now the air conditioning is blasting, the music is blasting, and I can't see anything because of the windshield wiper fluid.
Okay, do it. Do it. Kill the engine.
So we're killing the engine right now.
It says park sense. Actually can't accelerate. I stomped on the gas, but the Jeep slowed to a crawl. It says 43 miles an hour, but I'm not going that fast. I turned on my hazard lights, but I was still stuck in the right lane with no shoulder to escape onto. Guys, I'm stuck on the highway.
What did he say? I don't know, I think he's panicking. He's not gonna be able to hear us with that radio. It's so loud.
Guys, I need the accelerator to work again.
The accelerator will work. It won't work!
You're doomed.
Seriously, it's dangerous. I need to move.
You gotta turn the car off!
Okay.
Now you should be good to go.
So as you can see, it doesn't take much to hack a vehicle. if you think about your keyboard on your computer, when you hit that key on your keyboard, all you're doing is sending a signal from the key to the ECU that's sitting in your laptop that tells your computer to go do something. And the same thing happens with the vehicle. All you're doing is sending an electronic signal to say, go turn on the windshield wipers. You know, so it's really, once you understand how that all works, it's really not that difficult to manage and to figure it out. The problem becomes is, how do you prevent people from doing that? And the way we prevent people from doing that is putting all sorts of security on the vehicle itself. The components, the ECUs have operating systems. On some of them, we run an operating system called QNX, which is a Linux-based derivative. And we do those things, the same things that we would use to secure Linux, we would do the same on QNX, as well as RTOS, or real-time operating system. Now, these operating systems are not only used on vehicles, but they're also used on medical devices. They're used on the space station. They're used on gas pumps. They're used on surgical robotics suites. So it's just not the vehicle that we're talking about when we talk about securing an embedded system. All right, this is a real interesting hack. This is a relay attack. And what happens is, you know, your key fob uses radio frequency, and you can capture that radio frequency and send it back to the fob, in other words, to unlock the vehicle. So basically, you're mimicking and impersonating the fob itself. And so this is out of Manchester, England. The UK has a big problem with thefts of this nature right now, more so with commercial vehicles. And so they're going to use what's called a relay box. And so what they're doing is they have two boxes. So one guy stands next to the vehicle, and another guy is going to go and scan the house looking to wake up the fob and get it to send its signal. Once he finds that fob, it's going to send its signal to the vehicle. Boom, they open it up just that quick. But it only happens one time, right? And so he says, oh, I forgot to start the vehicle, right? So now he's got to go back and do it again. And he's going to pick up that fob signal so that the car thinks the fob's in the vehicle. The guy's going to push the button to start it. And off he goes. Now, this is a one-time attack, you know, because once they move away from that fob, they're not going to be able to recreate it. But people don't steal vehicles to sell them, right? People don't steal vehicles to use them. They steal vehicles to sell them. They're going to strip it down and piece it out and sell it on the market. This was in 2019. This is still a problem today. We do have ways to prevent it, and that's coming to market. It should be already out in the market, 2023. So what's the difference between an autonomous vehicle and a connected vehicle? An autonomous vehicle has the ability to drive and understand its environment versus a connected vehicle, which is just connected like any other computer system, you know, to the internet or to each other. Just because a car is connected to each other doesn't mean it's autonomous, all right? A car can be connected to a traffic management system. It can be connected to a building. It can be connected to other cars. That does not mean it's autonomous. Autonomous happens when it can drive by itself. In other words, I can take my hands off the wheel and the car understands its environment and drives and makes decisions on its own. We're at about level 2 autonomy. You're starting to see that now, with the advanced cruise control, where the car can slow down and speed up based on the cars around it. So if traffic slows down, the car slows down. There are cars that you can go hands-free now, some of the GM, some of the Ford cars. You still have to be alert, driver-facing cameras paying attention, and the car will change lanes and merge in and out of traffic and do those things. But you still have to be ready to take control of that wheel, because we're not quite there yet. Tesla Autopilot, Tesla gets away with it because when you sign your Tesla contract, you're saying that you understand that Autopilot is in beta mode and that it may cause accidents, and you are taking responsibility for that. For whatever reason, Tesla likes that model. You know, GM, Ford, Stellantis, Lucid, Nissan, Toyota, they don't want to take that model because they have a big brand to protect, right? We talked about brand. And this is where we get to full automation. We're not there yet. We're probably, if I had to guess, I'm looking at model year 26. I would say by model year 28, 29, 30, we'll probably be very close, if not at full autonomy. Here in Michigan, they are developing an autonomous corridor going from downtown Detroit all the way to U of M. It's about 20, 25 miles, and where autonomous vehicles are going to be able to drive in complete autonomy on these corridors. And they are enhancing the road system so that it's communicating with the vehicle and all of those things. This is what we talk about V2X communication. So vehicle to anything, whether it's a pedestrian it sees, a satellite system, an infrastructure, vehicle to vehicle, we make no distinction. It's just an object. The big interesting thing is going to be this traffic management system, because not only do these two vehicles have to be secured, but the infrastructure has to be secured, signage has to be secured, traffic management has to be secured, emergency management has to be secured, satellite systems. In order to get to full V2X communication and autonomy, all of these things have to happen. And oh, by the way, they have to have the laws put in place and the regulations and the insurance and all of those things. There's a lot of moving parts right now. But from a technology point of view, we're pretty darn close. So these are the SAE, or Society of Automotive Engineers, level of autonomy. And we are somewhere between 2 and 3 right now. We still have to take control of the vehicle, but the vehicle's doing more and more. When we get to level 5, this is when the vehicle is fully autonomous. I can nap, I can eat my lunch, have a conversation, read a book. So the vehicle connectivity, we talked about CAN. This is a very good representation of the networking in a vehicle. And as we said, everything's connected in the vehicle, from your mirrors that automatically adjust when you get into the vehicle, to your seats, to your engine system, your air conditioning, your heating, your cooling, your defrost, all of it. It's all just a connected computer system. So why do we need cybersecurity in vehicles? Well, we just showed you what the attack surfaces were, and we showed you that attack's actually in motion, and it's only becoming more and more prevalent. So with that, to talk about my program at Detroit Mercy, we do have master's programs. We have a graduate certificate program in vehicle cybersecurity, and this is a 15-credit course. And as you can see, the class I teach is Intro to Vehicle Cybersecurity. So basically, I take this presentation and we take a deep, deep, deep dive into each one of these topics, and do threat modeling and all of those things. We look at the vehicle electronics, automotive electronic systems. So we're very focused on this automotive embedded system. And then we have a master's program as well, where we look at hardware, we look at wireless networks, data science, because remember, we're talking about AI in that vehicle for autonomy. And this is where machine learning and the data science and artificial intelligence is going to have to take over. Once we get to that level 5, it's going to be complete AI. And so we definitely look at that deep learning and data science piece of it. And then we finish it up with a capstone project. And basically, we prepare you to go to what's called Cyber Auto Challenge and compete with other universities on hacking a vehicle. And it's here in Michigan, there's Cybertruck Challenge as well for the commercial vehicles. And the OEMs, or original equipment manufacturers, give us vehicles to hack. And so the capstone project prepares you for that. And then you compete with other universities. So that's our program. And the bachelor's program, the 5-year bachelor's to master's program, should kick off this fall. We're waiting for approval on that. And that is electrical engineering with a master's in vehicle cyber, mechanical engineering with a master's in vehicle cyber, or computer science with a master's in vehicle cyber. So with that, that's the end of my presentation. If anybody has any questions, I think we have a few minutes left. I know I covered a lot in a very, very short amount of time.
Yeah, James Crabb here. I think automated vehicles is a really interesting specific case of cybersecurity. I'm wondering, you mentioned earlier on in your talk, like policy and law, where is our government on, or what stances have they indicated that they're going to be taking on regulation of autonomous vehicles?
So originally in 2021, the European Union, the UNECE came out with regulation called WP29 I-155, 156. 155 secures the vehicle for the 17 European nations, and 156 secures the back end for those 17 nations as well. From the United States point of view, it's the word on the street is that the United States is going to be following suit to WP29, although it won't be a full regulation because the United States is more of a self-governing, self-regulating body. In other words, they won't put laws in place that says you cannot manufacture like the European Union did. But if you're in violation of any of the standards or the regulations, then you can be held criminally responsible. So in the European Union, they actually said if you don't pass audit, if you don't get vehicle type approval, you cannot sell vehicles in the 17 member countries, which includes Australia, Japan, all of the European countries. You know, so it's really a non-starter to say you're not going to meet the regulation.
Other questions? I have one. Has Tesla gotten better? They've got so much bad press, you know, about their vehicles, and I haven't heard as much lately. I used to hear it clearly. There was another crash.
Yeah.
So what's it?
Tesla's the gift that keeps on giving, right? From a security point of view. Just today, I've read that they had an insider threat, and a significant amount of data was given to the German media. So we're waiting to see that. Recently, there was a recall on a Tesla because of a camera. The GPU was failing. So in the US, they do regulate the rear view camera, and the rear view camera has to be functional and available to the road user in 2 seconds from the gear shift to reverse. And Tesla's GPU was failing, and that rear camera wasn't coming up. And so NHTSA forced them into a recall.
And then I heard about another type of hack where, I don't know if it's really like an actual hack, but where people would drive into like a truck stop and think they locked their car, but they override all the signals by, you know, putting out real strong interfering signals of a similar wavelength.
Yep, you can
And-
do that. Yep. It's not really, all right, so this is where we get into something called SOTF, safety for the intended feature or function. And by nature of some of the components in the vehicle, they work on radio frequency, and they are subject to signal interference. And the LiDAR, the radar, the ultrasonics, all of them are subject to signal interference. And so it's not really a hack, but it's something that we need to put in measures to prevent interference. And that really falls under a functional safety versus a security. And you'll hear me say this all the time, you know, you cannot have safety without security. I cannot make functional safety, but I certainly can break functional safety. And this would be an example of that, where I would have a device that would emit some frequency that would interfere with the components of the vehicle. So is it a functional safety problem? Is it a security problem? I don't know. It depends on what the motivation is.
Yeah. Okay, very good. Andrew,
I don't have a question. I think there was a question in the chat.
question in the chat. Okay, how do we get to it?
Let me see. It says, Clemente, in slide 15, you showed the architecture of a car, ECU, CAN bus, etc. Is there a reference to a standard architecture, or do manufacturers use their own proprietary? The manufacturers use their own proprietary, but we are moving more towards a standardization called zone architecture. And so basically, you'll have like the gateway up front that will be the brains of the operation. And depending on what the criticality are the components, you'll put it on various zones. You'll have a high secured zone and a low secured zone. And so we are moving into that zonal architecture, but internally, the way it's configured and the ECUs, the power of the ECUs, the number of cores on an ECU, it's really manufacturer dependent.
Okay. Well, thank you very much. Let's give a big hand to